Now so far we've seen a lot of vectors that are dealt with in some manner similar to this. There's some expression of a magnitude and an angle given. And that's all well and good, that's all the information we need to deal with a vector. However, it's sometimes not always the most convenient form to work with, particularly if we want to be able to easily put something into an equation. This basically represents an arrow pointing up and to the right. It's not super easy to put an arrow into the equation, and that's why we developed the process of breaking the vector down into components. You've seen this before. Here's the vector of magnitude 10. It's at an angle of 30 degrees with respect to the horizontal, which is the assumption if it doesn't say otherwise. And we've seen before breaking this down into a horizontal and a vertical component. And we've seen how you can go about calculating these, sine and cosine. We know that the adjacent leg of this triangle has a magnitude of the hypotenuse times the cosine of the angle. The cosine of 30 degrees is about 0.87, so 10 times that is about 8.7 for the magnitude of the horizontal leg. Likewise, the vertical leg is the opposite side of this angle, so we'll have a magnitude of 10 times the sine of the angle, since 10 is the hypotenuse. Sine of 30 degrees is exactly 1/2, so half of 10 is 5. So we've seen all that before. We've seen breaking this vector down into components, and that's all well and good. However, sometimes it's easier just to approach vectors as components from the get-go, and essentially treat them as components all the way from start to finish. And to accomplish that more easily, we have a little shorthand for writing a vector in the form of its components. And it looks something like this. I might say that this same vector, vector A here, one whose magnitude is 10, whose angle is 30 degrees, and whose x and y components are 8.7 and 5, respectively. I might say that vector A consists of, or equals, an 8.7 magnitude vector in the x direction, and also plus a magnitude 5 vector component in the y direction. I'm going to erase this triangle now to give us a little more room. But you can always rewind if you want to see it again. Alright, well this is basically what I just had here drawn as the triangle. Vector A is this x component and this y component. And then so we come up with a little shorthand to mean in a certain direction. For vectors, there's a particular symbol that means in a particular direction. It's a little hat or a caret. Sits up above the vector's name. Where this is simply some sort of generic vector, this means, in particular, this is what we call a unit vector. Where unit means 1. So this is a vector whose magnitude is always equal to 1, but whose direction is in a particular direction. In this case, a hat, which is how you generally read this, is a vector that points in the direction of A, but whose magnitude is 1. The reason for that is so we can essentially kind of break apart the magnitude and the direction of the vector separately if we needed to. The magnitude, 10, is an easy number to write down, but this kind of a hat is a shorthand for representing pointing in a particular direction. Now that's not always incredibly useful. What's most useful is when we do that for vectors whose directions we use a lot. In other words, we could write a unit vector in the x direction, and I might just write an x with a little hat on it, to represent a unit vector, vector of magnitude 1, pointing in the x direction, that is along the x-axis. And likewise, I might define a vector that means in the y direction with a unit vector labeled as y hat. The point of them being unit vectors, of them being magnitude 1, means I can use them for purposes like what I've written here. I could express vector A as being some magnitude of a component vector multiplied by a unit vector. So this together is a vector itself. You know, the components of vectors are also vectors. They just only point along the x-axis or the y-axis or the z-axis. So here's a vector. Its magnitude is 8.7. We're multiplying it by a unit vector whose magnitude is 1, so don't change the magnitude any. It ends up being 8.7, and whose direction is along the x-axis. In other words, this is a vector whose magnitude is 8.7, pointed along the x-axis. And likewise, this part is a vector whose magnitude is 5 and pointed along the y-axis. So what I've done here is written a shorthand for this x component vector and this y component vector, which we've just seen a second ago, are the vectors that make up vector A. However, we take one more little step from here, because x and y and z are variables that come up all the time in problems. And so we don't want to introduce extra x's and y's and z's. It might be a little bit confusing. And so what we're going to do is we're going to replace these with some letters that very rarely come up in problems, so it's a little less confusing. So one of the least common letters to be used as a variable, at least in math and physics, is I. And so we call the unit vector in the direction of the x-axis I hat. And then in the way that x, y, z proceeds alphabetically, we'll proceed alphabetically from here. The y-axis, its direction will be represented by a vector j hat. Notice that the traditional way of writing these is for the hat to replace the little dot above it, so the little dot above the I and the j are gone. And likewise, if we had a z component, it would be k hat. Now this doesn't mean anything different than what I've written right above it here. This still means vector A consists of a vector component that's 8.7 along the x-axis in the x direction, and 5 along the y-axis in the y direction. It's just a slightly different way of writing it. And so we would say that this vector is an equivalent way of writing this vector. We've just written it in components, or sometimes in what's called IJK notation, because of the unit vectors I hat, j hat, and k hat that represent x, y, and z. We'll look at the next video as to how you would use this and why you would care.